Somewhere in the vast darkness of space, there exists a star that should not exist. It is not just powerful, it is catastrophic in a way that defies imagination. If it were to drift even halfway across our galaxy, it wouldn't simply destroy planets. It would begin to tear apart the very atoms that make up everything around it, including you. Far beyond that, there is a region of the universe so empty that it challenges our understanding of reality. It is not just a place with fewer stars or distant galaxies. It is a massive cosmic void where almost nothing exists at all. No clusters, no light, just an eerie, expanding emptiness that seems to contradict how the universe is supposed to distribute matter. And deeper still, astronomers have discovered galaxies, massive, fully formed galaxies, that appear far too early in the history of the universe. These structures exist at a time when the universe was still in its infancy, when such complexity should not yet have been possible. It is as if something rushed the process, or ignored the timeline completely. These are not ideas pulled from science fiction. They are real observations, confirmed by scientists and powerful telescopes. And they all point toward one deeply unsettling truth. They should not exist. Because the universe, as far as we understand it, follows rules. Rules that govern time, space, matter, and energy. Rules that have been tested repeatedly and have explained nearly everything we observe until now. Yet out there, in the silence of deep space, those rules appear to be breaking. The question is no longer just what exists in the universe. The real question is why these impossible things exist at all. To understand what makes these discoveries so disturbing, we first need to understand the rules they seem to violate. The universe is not completely chaotic. Beneath its complexity lies a framework of laws that define how everything behaves, from the smallest particles to the largest galaxies. One of the most important breakthroughs in understanding these laws came from Albert Einstein. His work revealed that space and time are not separate entities but are woven together into a single fabric known as spacetime. Massive objects like stars and planets bend this fabric, and that curvature is what we experience as gravity. This explains why planets orbit stars and why galaxies hold their shape. It is a system that operates with incredible precision. But there are limits, strict boundaries that cannot be crossed. One of those limits is the speed of light. According to everything we know, nothing in the universe can travel faster than light. This is not just a technical limitation. It is a fundamental part of how reality is structured. If something were to exceed this speed, the cause and effect relationship that governs events would begin to collapse. Another fundamental principle is entropy. It describes the natural tendency of systems to move from order to disorder. Over time, stars burn out, structures decay, and energy spreads out evenly. In simple terms, the universe is gradually winding down, not building itself up spontaneously. Then there is the timeline of the universe itself, which began with the Big Bang. From that moment, everything followed a sequence. First came subatomic particles, then atoms, then stars, and eventually galaxies. Each stage required time, millions or even billions of years. This timeline is critical because it defines what should exist at any given point in cosmic history. But when we look into deep space, we are not just looking across distance, we are looking back in time. And what we are seeing does not always match what should be there. We are finding objects that form too early, evolve too quickly, or behave in ways that challenge these fundamental laws. This raises a disturbing possibility. Either these rules are incomplete, or our understanding of them is fundamentally flawed. At the center of nearly every galaxy, including our own, lies one of the most extreme objects in existence, a black hole. These are regions where gravity becomes so intense that nothing can escape, not even light. They are formed when massive stars collapse under their own weight at the end of their life cycles, compressing into a point of infinite density known as a singularity. Surrounding this singularity is a boundary called the event horizon. Once anything crosses this threshold, there is no return. Even light, the fastest thing in the universe, cannot escape its pull. While black holes themselves are already difficult to comprehend, the real mystery begins when we look at their size. Some black holes are not just massive, They are supermassive, containing millions or even billions of times the mass of our Sun. What makes this truly puzzling is when and where we find them. Observations from organizations like NASA have revealed supermassive black holes existing in the very early universe, less than 1 billion years after the Big Bang. This creates a serious problem. According to our current understanding, black holes grow over time by consuming matter and merging with other black holes. This process should take billions of years. And yet, these enormous objects seem to have formed far too quickly. It is as if they skipped the growth process entirely or were born already massive. Either scenario challenges the laws we rely on to explain how the universe evolves. It is as if they skipped the growth process entirely or were born already massive. Either scenario challenges the laws we rely on to explain how the universe evolves. If these black holes truly formed faster than the universe allows, then something is missing from our understanding. Either the physics behind black holes is incomplete, or the timeline of the universe itself is not what we believe it to be. And this is only the beginning of the mystery. If black holes represent gravity at its most extreme, then magnetars represent something equally terrifying. Magnetism pushed far beyond what should be possible. Magnetars are a type of neutron star, the collapsed core left behind after a massive star explodes in a supernova. These remnants are already extreme. They pack more mass than our Sun into a sphere only a few kilometers wide, creating densities so intense that a single teaspoon of their material would weigh billions of tons. But magnetars go further. They possess magnetic fields so powerful that they defy comprehension. These fields are trillions of times stronger than Earth's magnetic field, so strong that they can distort the very structure of atoms from thousands of kilometers away. In normal conditions, atoms are stable. Electrons orbit nuclei in predictable ways. Chemistry, matter, and life itself depend on this stability. But near a magnetar, those rules begin to break down. Magnetic forces become so dominant that they stretch and deform atomic structures, turning ordinary matter into something unrecognizable. Even light is affected. Photons, particles of light, can be twisted and polarized simply by passing through a magnetar's magnetic field. Space itself begins to behave differently. And then there are starquakes. This should not happen. According to our models of cosmic evolution, matter in the early universe should have spread out in a way that eventually formed structures everywhere, even if unevenly. Large empty regions are expected, but not on this scale and not this empty. The Boötes Void challenges that expectation. It suggests that something prevented matter from forming there, or perhaps pushed it away entirely. Some scientists have proposed that it may have formed from the merging of smaller voids over time. Others suggest that unknown processes in the early universe created regions where galaxy formation was suppressed. But no explanation fully accounts for its size and emptiness. Standing at the edge of such a void, if that were possible, you would see almost nothing. No nearby galaxies lighting up the darkness. Just a vast, stretching emptiness in every direction. It is not just empty space. It is a region where the universe seems to have skipped a step. And that raises an unsettling thought. If something can create a void this large, what else might the universe be capable of removing? In the vast halo surrounding our galaxy, astronomers identified a star that seemed, at first, completely ordinary. It was faint, ancient, and composed mostly of hydrogen and helium, characteristics typical of some of the oldest stars in the universe. But when scientists began to measure its age, something didn't add up. This star, known as HD 140283, appeared to be over 14 billion years old. That might not sound unusual, until you consider that the universe itself is estimated to be about 13.8 billion years old. In other words, this star seemed to be older than the universe it exists in. At first, this result was met with skepticism. Measurements in astronomy are incredibly complex, and small uncertainties can lead to large differences in calculated ages. Scientists revisited the data, refined their models, and improved their instruments. The estimated age was adjusted slightly, bringing it closer to the accepted age of the universe. But even with these corrections, the star remains uncomfortably close to that limit. It sits right at the edge of what should be possible. This creates a subtle but profound tension. If the measurements are correct, then our understanding of stellar evolution or cosmic timelines may be incomplete. If the measurements are off, then it reveals how difficult it is to truly measure time on a cosmic scale. Either way, the Methuselah star highlights a deeper issue. We assume we understand the sequence of events that followed the Big Bang. We believe we know how long it takes for stars to form, evolve, and age. But when we find objects that push those limits, it forces us to question how precise that timeline really is. Time, at least on a cosmic scale, may not be as straightforward as it seems. And if time itself is uncertain, then every event in the universe becomes a little harder to place. For most of history, space was silent. Not literally silent, but predictable. Signals detected from space, radio waves, light, radiation, could usually be traced back to known sources like stars, galaxies, or energetic events such as supernovae. Then something unexpected appeared. Short, intense bursts of radio energy, lasting only milliseconds, began to show up in our instruments. These events were incredibly powerful, releasing as much energy in a fraction of a second as the sun does in days. They became known as fast radio bursts, or FRBs. At first, they were dismissed as interference, possibly even errors in our equipment. But as more were detected, from different locations and observatories, it became clear that they were real. And they were coming from far beyond our galaxy. Some FRBs occur only once, never to be seen again. Others repeat in irregular patterns, as if something is turning them on and off. Their origins remain largely unknown. Some theories suggest they are caused by extreme astrophysical objects, such as magnetars or colliding neutron stars. Others propose more exotic explanations involving unknown cosmic processes. What makes FRBs so unsettling is not just their power, but their unpredictability. They appear without warning, from random directions, and vanish just as quickly. There is no clear pattern that explains all of them. It is as if the universe is sending out brief, powerful signals, without revealing their source. And until we understand what is producing them, they remain one of the most mysterious, and potentially important, phenomena in modern astronomy. Up to this point, every mystery we've explored has involved something extreme, objects that are too powerful, too old, or too empty to make sense. But the next anomaly is different. It is not something we can point to in the sky. It is something we cannot see at all. And yet, it dominates the universe. When astronomers observe galaxies, they expect stars near the edges to move more slowly than those near the center. This is how gravity works. The farther you are from the mass, the weaker its pull should be. But that's not what we see. Stars at the outer edges of galaxies are moving far faster than they should. So fast, in fact, that they should be flung into space. And yet, they remain bound, orbiting as if something unseen is holding them in place. This something has been named dark matter. It does not emit light. It does not reflect light. It does not interact with normal matter in any way we can easily detect. And yet, its gravitational influence is undeniable. Without it, galaxies would not exist in their current form. Even more unsettling is dark energy. While dark matter holds things together, dark energy is doing the opposite. It is causing the expansion of the universe to accelerate. Galaxies are not just moving away from each other, they are speeding up as they do so. Instead, we are seeing large, structured systems that look far more mature than expected. It is as if the universe accelerated its own development. These discoveries raise difficult questions. Did galaxies form faster than we thought? Were the conditions in the early universe different from our models? Or is there a missing piece of physics that allowed matter to organize itself more quickly? Each possibility points to the same conclusion. The timeline of the universe may not be as reliable as we believed. And if the sequence of cosmic history is uncertain, then everything built upon that timeline, from star formation to galaxy evolution, must be reconsidered. Individually, each of these discoveries is extraordinary. A magnetar with impossible strength. A void too empty to explain. A star that seems older than time. Signals with no clear origin. Galaxies that form too early. And an invisible universe we cannot directly observe. But when viewed together, a pattern begins to emerge. These are not isolated anomalies. They are consistent contradictions. Again and again, we encounter objects and phenomena that push against the boundaries of what should be possible. They do not exist before. For centuries, humanity has tried to understand the universe by building rules, models that explain how everything works. And for the most part, those rules have been incredibly successful. They have allowed us to predict planetary motion, harness energy, and explore space. They have given us a sense of order in a universe that once seemed chaotic. But what we are beginning to see now is something different. The universe is not just complex. It is unexpected. Every time we push our observations further, looking deeper into space, earlier into time, or closer into extreme conditions, we find something that challenges what we thought we knew. Not in small ways, but in fundamental ones. It is tempting to think of these anomalies as problems to be solved, errors to be corrected, or exceptions to be explained away. But what if they are not exceptions? What if they are clues? Clues that point toward a deeper reality, one that we have only just begun to glimpse. Perhaps the universe is not breaking its own rules. Perhaps we have only discovered a small part of them. And everything we call impossible is simply a sign that our understanding is still incomplete. In the end, the most unsettling truth is not that strange things exist in the universe. It is that we expected them not to, because that assumption reveals something about us. We believed we understood the rules of reality. But the universe is under no obligation to match our expectations. And out there, in the vast darkness beyond our world, it continues to create things that challenge everything we think we know. Things that shouldn't exist, but do.